Okay. Hello everyone and welcome to today's QDB Engineering webinar. My name is Bonusri Dotto and I will be your host for today's session. We are going to explore database branching at Kubernetes scale. In today's webinar, we will look at how KubeDB database branching can create fast, isolated Postgres environment across Kubernetes cluster using snapshot-based copy on write, OCM, and shared SAP storage. We will also have a live demonstration where you will see all of these things. Okay, today's session will be presented by Anisur Rahman, staff software engineer at AppsCode. Anisur, thank you for joining us today. I will hand it over to you to get started.
Uh, Thank you, Bonusri Dotto. Okay, I will start today's webinar. My name is Anis Rahman. Currently, I'm working as a staff software engineer at AppsCode. In today's webinar, we will see the database branching in across multiple Kubernetes cluster. The branching actually is possible only for by using a control plane architecture for creating isolated Postgres environment across multiple cluster without copying the full database. So in today's session, we will see the architecture and the live demonstration. This feature stands for four tools actually. The first tool is KubeDB, which is our product, our AppsCode native product, and the KubeDB is used for the database lifecycle management. And the second tool we used in this feature is OCM. OCM means Open Cluster Management. This is another open source tool used thanks to the OCM team for these useful tools to make it open source. And the third one is Kubernetes to run the database on cluster. And the last one is the storage layer. Uh, In this session, we will use the safe storage as a shared storage across multiple cluster. We can use various storage, not only safe. We can use ZFS. We can use any storage layer actually. Before diving to the branching feature, we have to know that how actually the branching make it working actually under the hood. The branch is actually just cost a metadata only, not the full database copy. So under the hood of branching, there is two way we can copy the entire file system of any storage layer. The first one is the convention layer, and the second one is copy on write over time. So in in this slide, we will first try to understand what is copy on write and what is the conventional clone actually. The conventional clone is actually read the source file system every block manually and then transfer this data across the network. It can be same cluster, it can be different cluster, or might be in different region. And then on the target cluster, you write in a block of the file system. So there, this is used costly way because we have to move the data across network. We have to read, we have to write everything. We have to do that. So for the large scale database, for example, 500 GB or 1 TB, it's really took almost 8-9 hours, and even might be taken about 12 hours and more. But what is the technology on copy on write so that we can clone the file system within 2 or 3 seconds, whatever the size, it doesn't matter actually. If the size is more than 1 TB, we also can clone the entire database within 3-4 seconds. How actually it possible? The main architecture of behind it actually the storage copy on write. So how the storage copy on writes, let's try to understand with me. So there is three phase. The first phase is before a snapshot. The second phase is after a snapshot, and the third phase is modification. So let's think about you have a file system on your Linux machine, and this is your current file system, and there is some data on your file system, and the file system actually work behind it as a block by block. The block size can be 4 KB to 64 KB. The traditional, the modern storage layer always try to maintain that convention. So for example, this is the 4 KB storage block A, B, C, and D. So the storage on your current file system, there is 4 storage block. And let's take a snapshot, copy on write snapshot of your current file system. So when you take the snapshot of your current file system, the snapshot points to the same block that was in your current file system. So how actually it behind working, it actually pointing to the same block. You can see the graphical view. The snapshot device also pointing to the same block of the current file system. So they under the hood, they are pointing to the same inode. Inode is a concept of storage layer. So when you might ask me the question actually, when you modify any block, does the modification or will also go to the snapshot? They have, for example, there have so many snapshots. So the answer is no actually. So that's why the name comes from copy on write. So after modification, let's think here. Let's focus here. After you modify the D block, what will your current file system will do? The current file system will first copy the D block to a different inode. The file system will check that of the D block have how many inode are holding of this D block metadata actually. So if the inode is greater than 1, that's mean some more snapshot or device block also pointing to the same block. That's mean I don't have to authority to entirely write here because someone of the snapshot also pointing there. So what I have to do, I have to copy this block, and after the copy is done, then I will write inside it actually. That's why the naming comes from copy on write. First copy D, then to a different inode, then write here actually. This is the graphical actually shows. And there is, if you add the new data on the current file system, they will be separated, and the snapshot is as it was. So this is how the storage layer works in modern Linux file system. So this is this is how there is the data plane hands off. In this slide we will try to understand how the cross cluster storage is working. So the branching feature only possible when you have configured the clusters with a shared storage. This is not the credit of the CSI driver. This is the fully credit of the storage layer. So in our session, we are using the shared safe storage. You can think if as a different cluster, which is not to the source cluster and the target cluster. So this is a different safe cluster. And this cluster is using as a CSI driver for the source cluster and also for the target cluster. So source and target both are using the same shared uh, storage. Now, when we take a volume snapshot of the source PVC on the source cluster, then the volume snapshot, the CSI driver will create a volume snapshot content, and inside the volume snapshot content, the CSI driver store the snapshot handle ID. The snapshot handle ID is unique device storage device ID, which comes from the shared safe storage. That means this snapshot handle ID can also accessible from the target cluster. So when on the target cluster, if we create the volume snapshot content by referring to the same snapshot handle ID. Then create the volume snapshot by referring the volume snapshot content. Then we can create the PVC from the volume snapshot. So this is so easy, right? We only transferring the metadata from the source cluster to the target cluster. So it's quite easy. It's only need 2 or 3 seconds to make it happen between the cross cluster. So here, this is another tool what we need. We used in our branching feature, which is OCM. This is the great tool. Using the OCM, we can manage multiple child cluster or the managed cluster. So OCM stands for actually managing multiple cluster by using a single cluster. So here on the diagram, you can see there is a hub cluster and there is a uh, managed cluster. So these managed cluster are managing from the hub cluster. So how the managed cluster join to the hub cluster? This happened at the first stage. At the first stage, the hub cluster create a bootstrap kubeconfig, and the managed cluster use a clusterlet ID, clusterlet binary. With it, uh, it can send a join request by using this bootstrap kubeconfig to the hub cluster. Hub cluster has a registration controller which actually accept the request, uh, approve the request of the managed cluster. Then the hub cluster can manage the managed cluster. How the hub cluster manage the managed cluster? When the registration process succeeded on the hub cluster, there is a namespace for this cluster name. So the managed cluster always watch this namespace. So when the namespace on that namespace, if hub cluster create a manifest work, the managed cluster watch it continuously and then apply on this cluster. So this was a basic architecture of OCM. It's a broad stuff. So in today's webinar, we only focus on the basic part of the OCM. Uh, i- Now let's talk about how branching feature work in distributed cluster and how it manages by OCM. Let's think about there is 3 cluster. One is source cluster, one is hub cluster, and one is target cluster. So from the hub cluster, both cluster are registered to the hub cluster. That's mean the hub cluster can manage these 2 cluster. Now source cluster and hub both are using the same safe storage layer. So there we have some custom resource in our operator, branching operator. So for example, there is a branch CR. So under the branch CR, you can refer the cluster name. So for example, there is a cluster name is target, and this is the target cluster. So when you create a branch CR on the source cluster by referring a database, the branch operator continuously watch this branch, and it watch the database also, and it create the snapshot of the database. It can take volume snapshot and volume group snapshot for high available database. For example, the Postgres have 8 replica or 9 replica. Then how to make it consistent? So to make it consistent, our operator always take volume group as snapshot at the same time for all the privacy. So this is how we make it consistent. Then when we take the volume snapshot, we have to uh, transfer the YAML to the target cluster with database also. So that's why we have introduced a custom share, which is branch work, and the hub cluster using uh, OCM add-on template. That's so that the hub cluster have access to create a manifest to the OCM hub cluster. So the source cluster operator create a branch work on the hub cluster. So on the branch work, there are so many manifest. For example, the database manifest, volume snapshot manifest, and everything what we have to need in target cluster. So the hub cluster reconciler watch the branch work and create the manifest work on the target namespace. The target namespace continuously watched by the target cluster. So the target cluster creates the volume snapshot content first, then the volume snapshot, and the database essential secrets, config map, everything, and then it creates the uh, database YAML on the hub cluster, and kubedb is the live operator provision make ready to this cluster database here. So this is how actually the branch is working. So our branch have so many feature. For example, there if we consider the placement, it support same cluster with the local reconciliation. There is no hub spoke model. So basically, inside a single cluster, you can create branch of any database, which is kubedb manage. The second is actually the cross cluster. So by using OCM hub and managed cluster model, you can clone the database across many cluster you want. And it also support the cross namespace. If, for example, you have a dev namespace, so where you want to create the database, it also possible with it. Now, if we talk about the feature, what we have for the branch, then that first will come the snapshot backend clone, which is two-way write isolation, and the second one is the refresh. That means on the branch here you can assign the cron expression, so that on this cron expression the uh, branching will be refreshed, so that it will continuously take volume snapshot on the source cluster and clone it to the target cluster. And there is another feature which is actions. You can run any post action job on the hub cluster. It's also a necessary feature. For example, you want to delete some database, some table on the target cluster, because those are so much sensitive. So for the testing, analytic, or debugging, you do not need it. So, or you don't want to give that permission to any user. So that's why you want to delete it. It's also a great feature. The last one is credential. So you don't want to expose the credential what you are using on your source cluster. So you can rotate the credential also. And there it also support, not only support the standalone, but it also support the high availability databases, which comes with replication. And the last feature is actually the retention. You can delete or make it delete or orphan. If you delete the databases on hub cluster, source cluster, it will not delete to the target cluster. So this is how actually the branching feature comes. And this is our live demonstration session. So for the demonstration, we need kubedb, we need courier API, we need OCM, and also a shared safe RBD. So I'm going to share my terminal to start a demonstration. Uh, this is my terminal, and we have three cluster, and the first one is source cluster. This terminal I will use to watch the YAML resources from the source cluster, and this is another terminal here we will use for watching the target cluster manifest. And this is my general terminal actually. So for the simplicity, I have created the source target cluster and join them to the from the OCM. So to reduce the webinar time actually, let's verify it. Uh, so I have created, let's check that these two mm, database are in our hub cluster. Let's list the managed cluster of from the hub. So you can see from the hub side, this is the hub cluster. On the hub side, there is two databases, two cluster on each source and on another one is target. Both are joined is equal to 2 and both are available. So from hub, the hub is managing two database, two cluster on each source and on its target. Now we have also created the safe cluster earlier. So as this is only for demonstration purpose, I created a safe cluster on a VM. It's a single node safe on OSD cluster, and both are accessible from the source and target cluster. So let's check the storage class of both cluster. So you can see that there is a safe RBD storage class present in source cluster, and this the same CSA driver is also exist on the target cluster. So both are using the same safe storage, which have created on a separate VM. So so till now we proved that we have a safe cluster on a separate VM, and we have source cluster which is using the same safe storage, and we have a target cluster which is also using the same safe cluster. And from on the hub side, we are managing the source and target cluster, and both are managed by hub cluster. Now let's check that I have created a demo Postgres on the source cluster. The hub cluster, the target cluster, there is no Postgres. I am watching the Postgres branch PVC volume snapshot manifest on the demo namespace on the target cluster. And you can see there is a Postgres. It is in ready state, and let's count the row of this Postgres. Here on the demo Postgres, there is almost 1 lakh row. So now let's talk about branch manifest. This is branch manifest. On the branch manifest, yeah, we are referring our demo Postgres as a database reference, and the database is in demo namespace. And on the target section, we are referring the target cluster name. That means it will resolve by OCM. So there can be so many cluster. So we are targeting the cluster name, which is target. And on the target cluster, we want to clone the database on the demo namespace, and database name will be different. Let's check here. On the source database, there is a demo PG, but on the target, we want to uh, change the database name. So I change it and I add 10 minute on the suffix. And we can also specify the storage class name, and we can also specify the resources. For example, that on the target source cluster, the Postgres is using 8 GB RAM, but we don't want to copy the entire 8 GB RAM. So we can customize it here also. And also we can set the schedule, as I said it earlier on the theory session, that we can set cron. Here I have set 10 minutes interval. That's mean in every 10 minutes our branch operator retake the snapshot from the source and 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 clone the databases to the target cluster. So let's apply this branch manifest and let's see what happened. So as I proved that yes previously that there is 1 lakh rows in our source Postgres. On the target there is no Postgres here. You can see there is no Postgres and nothing here. Now let's apply the branch manifest. So this will create the branch manifest to the source cluster. I mean here, you see that the branch is created on the source cluster and it's in snapshot phase. The volume snapshot is also taken. Within a second, the OCM created the manifest work on the hub cluster and the target cluster watch it and created the branch and the Postgres what we want, the clone Postgres on the target cluster. The Postgres is in provisioning state. Let's wait until it's go to the ready state. So uh, we can actually clone the entire database, not necessary the storage, how much the storage size is. You can see that the Postgres is ready and the branching is also ready. And the surprisingly, you can see that this branching is also ready. How does it happening? It happening actually the in the OCM there is a feedback rule. By using this feedback rule, OCM watch the branch here and watch the status of this branch here. So by using that feedback rules, it go back to the it shared to the source cluster and apply a manifest work and the source cluster watch it and update the branch here. So if I get the YAML of the branch here, you can see there is a mode actually. This is the initiator mode. That means it will take the snapshot and of the databases, and there is a creator mode. Basically, the target cluster, it will create the database on the target cluster. Let's get the branch here on the source cluster. So if I talk about the status field, you can see that let's go the status field one by one. So it uh, on the status field, we can see that the snapshot is in ready state. There is a condition for it. Then there is a refresh generation. So currently we are in only fast stage. That means the refresh generation is 0. The second is branch is ready. It comes from the OCM. And third one is target is also ready. So it also watch the target. And the last refresh time, we can see the refresh time, last refresh time. And also uh, on which PVC it take a snapshot, there is a subfield which is called member. So it also keep the reference for which PVC are take snapshot taken, and the phase is ready. So now we can check the freshness of the branch. This is 2 minute 37 second. That means within 10 minutes it will all also again refresh the branch actually of this database. So now let's verify that our branching working successfully. Let's row count of the target database. So you can see that there is that on the target cluster, I just use the context target. On the target cluster, there is also 1 lakh rows. So which proves that our branching working successfully. Uh, this was our today's webinar. Thank you everyone for joining.